Okay. Okay, so good morning. We continue today with the derivation of the microcanonical ensemble. And I think that last time we reached a point that was the following. Let me see if I remember where we were. So we derived the Liouville equation, which was the equation for the distribution function in the phase space, rho. And then we said that, let me see if you, can you see? Yes. Derivative of rho with respect to time plus the Poisson bracket of rho with the Hamiltonian is equal to 0, where rho is the distribution function. Now this is valid in general, so the rho, depending on pi, qi, and t, contains basically all the informations you need. But so also for situation out of equilibrium, out of thermodynamical equilibrium. Now in thermodynamical equilibrium, we said the rho must be stationary because it corresponds to our intuition of thermodynamical equilibrium, and therefore that means from the Liouville theorem that the Poisson bracket of rho with h must be equal to 0. And so there are different ways in order to fulfill this equation. One of the possibility is that rho is constant in a certain region of the phase space, which was gamma, and then rho is 0 outside this region. It must be in this way because in any case qi and pi are limited in the phase space because the energy is fixed and the volume is fixed. Then we say, okay, let us suppose that the rho is constant in a volume which is determined basically by the energy and by the uncertainty on the energy. So in particular, we have that rho is constant in a portion of the phase space for which the h, so the Hamiltonian, provides a value which is E plus delta half and E minus delta half, where E is the total energy and delta is a sort of uncertainty, small uncertainty on the energy, whereas rho is 0 elsewhere. Okay. So basically, this is an assumption that one does, which is Boltzmann statistical assumption that basically corresponds to the cases we were discussing, as I said many times, with the example of k-states and particles, and we said that all the states were occupied with the same probability. So here is a similar thing. Basically, all the microstates which are compatible with our constraints are occupied with the same probability, which is provided by rho. Okay. This equation basically is the definition of what is called microcanonical ensemble. Microcanonical ensemble. The ensemble is basically rho. Okay, so defining rho in this way, so rho is constant in a certain volume of the phase space compatible with macroscopic constraints, and rho is equal to 0 elsewhere, is the definition of what is called microcanonical ensemble. Okay. And then we will see two other kind of ensemble where I remind you the ensemble is basically well, a sample of systems which are basically the same system but in different microstates, each of them comparable with our macroscopic constraints. And the ensemble was a useful conceptual construction in order to derive averages. Instead of doing time averages of certain observables, we do ensemble averages. Okay, the main assumption of Gibbs is the fact that these two averages corresponds to each other, so they are the same. Okay, so now we need to work out an example of this microcanonical ensemble, and we start with the most simple case. Okay, so we take a gas of particles, n particles, volume V, total energy E, non-interacting, no external field, nothing. So basically the Hamiltonian, if the particles are all the same, particles with the same mass, which is the easiest situation, the Hamiltonian H is written in terms of just the sum of the kinetic energy. So it's 1 divided by 2m, sum from I to 3n of pi squared. Okay, so this is the Hamiltonian for a system made of non-interacting classical particles. All this construction is classical, okay, remember. So just kinetic energy. Now, the thing is that we said that rho occupies a volume or determines basically a volume apart from a constant, which is this omega. Rho, which is a function of qi and pi, and here we have d3 n q, d3 n p. So what we need to determine is omega, which is basically, since rho is constant, is proportional to the volume occupied by the microcanonical ensemble. Okay, so is the proportional to the volume occupied by the macrocanonical ensemble. Okay, and since we have a proportionality between omega and rho, because rho is constant, let's just put for a moment, let us set rho equal to 1 and rho equal to 0 outside, okay, in the region rho equal to 1, in which region? In the region determined in the phase space by these inequalities, E plus delta half and E minus delta half, whereas rho equals 0 elsewhere, as usual, elsewhere. Okay, so what we need to do, let me change page. Is the computation of this omega. And this is clearly done by the following equation. I have a v to the power of n, because this is the integral over d3 when integrating over d3 and q, we get a factor of volume, so n factors of volume for each particle. So we have just a v to the power of n. And then we have an integral which is d3np, where in the region determined by the constraints h smaller than e plus delta divided by 2 and a and h larger than e minus delta divided by 2. Okay, so this is the integral that we need to do. Now, what is this integral? Well, actually, since the Hamiltonian is 1 divided by 2m, the sum over pi squared, this region is a spherical shell. Okay. So if I do a plot, let me just put 3 axes. Let's say this is P1, P2, and P3. And the equation 1 over 2m sum from 1 to 3n of pi squared equal to E determines a sphere, of course, the surface of a sphere. And since this is less than E plus delta half and larger larger with respect to E minus delta half, basically I just have the shell, a spherical shell, which is somewhere here. Okay. Okay. So this is a spherical shell with radius determined r, which is the radius of the sphere, is just, by looking at this, is just square root of 2m times E. So this is the radius of the sphere. And we can determine also the size, the thickness of this spherical shell in terms of delta, okay? Because we have that p squared divided by 2m is equal to E, where I defined p squared to be the sum from 1 to 3n of pi squared. From this, 2p, so p dp is equal to divided by m is equal to dE, which is in turn, which is delta, is the uncertainty on the energy, from which dP is equal to m delta divided by p. But this was also m delta divided by square root of 2me, which is again delta square root of m divided by 2e times delta. And this is the dP, which is proportional to the delta, which in turn is also, if you want, the dr. So it's the thickness of the shell, of the spherical shell. Okay. So we have basically to compute the volume of a spherical shell in 3n dimensions. So what we need to do is to compute the volume of a spherical shell in 3n dimensions. Okay? So the canonical ensemble, microcanonical ensemble, at least in this case, in which we just have kinetic energy, corresponds to basically the volume occupied by a spherical shell in the phase space. So in 3n dimensions, not 6n but 3n, because we have already integrated over the coordinates. Notice, however, that this is, of course, the simplest case in which we just have kinetic energy. All the particles have the same mass. And this is, of course, the simplest case. In general, of course, if you have, for instance, interactions between particles, you would have also the terms depending on the coordinates, and of course the constraints that that the Hamiltonian is between E minus delta half plus and E plus delta half becomes much more difficult to determine. Okay, actually, the easiest case that we will also analyze later will be the ones in which the Hamiltonian is a quadratic form in P and Q, because in that case we know the shape of the if you want, the shape of the macroeconomical ensemble, which could be, in any case, a sphere or something very, very close to a sphere. Anyway, in this case, the situation is the following. We just need to determine the volume of a sphere in these 3n dimensions. Okay. Now, the rest of this part will be just geometrical derivation of the volume of a sphere in these dimensions, okay? But we can do some approximation. So first of all, suppose that you have new dimensions in general. The volume of a sphere of radius r is something like c, which is a constant, times r to the power of n. In 3 dimensions, the volume of a sphere is 4/3 pi r to the power of 3 in 3 dimensions. So in new dimensions will be something like c r to the power of nu. And suppose that now you reduce the radius by a certain amount epsilon and compute the volume of this sphere of radius r minus epsilon. Therefore, this will be c r minus epsilon to the power of nu. Therefore, the spherical shell has a volume. Spherical shell has a volume which is just the difference Vr minus V of r minus epsilon, okay? Which is equal to Cr to the power of nu, which I can collect, and then here I have a 1 minus, here you have a 1 minus epsilon divided by r to the power of nu. Okay, let me see if this is correct. If I multiply this by this, I get Cr to the power of nu, so Cr nu, so Cr there minus epsilon. Okay, it should be correct. Okay, so the r is in here, r minus epsilon, yeah, it's correct, okay? Now, if epsilon is small, because this spherical shell has a small thickness, I can approximate this by using an exponential. Well, actually, this part maybe is not necessary, but in any case, let's do it. So it will be an exponential of minus ER times nu. Okay? If epsilon is small, 1 minus epsilon r to the power of nu is approximated with, well, if you want, is it has the same, corresponds to the expansion of an exponential. Okay? Now, if epsilon nu r, now if epsilon nu is much larger than r, I can neglect this term here, and basically, let me change page. So if epsilon nu much larger than r, basically the volume of the shell is almost equal, to the volume of the sphere. Okay, which was C nu C r to the power of nu. Okay, so this means that when I have large number of dimensions, so this holds true, of course, it is correct for large nu. In this case, of course, nu is large because we have 3n dimensions, where n is the number of particles, so it's of the order of 10 to the 23, so it's a very large number. And now for large number of dimensions, you can basically all the volume of a shell is just at the end. Okay, so it basically corresponds to the volume of the sphere. Okay, this does not make any difference computing the volume of a sphere and the volume of a spherical shell when the number of dimension is very large. They are the same. Okay, basically because the volume of the sphere is dominated, if you want, by the outer layer. Okay, this is basically the reason. Now, why epsilon nu is much larger, is much larger in this case than r? Well, epsilon is a small quantity, but nu is a very large quantity because it's proportional to the number of particles, is 3n, whereas r was the square root of 2me. The radius was the square root of v of me. Now suppose that E, well, in this case, E contains the sum of the kinetic energy of all the particles. And if all those energies are the same, equipartition, if you want, equipartition theorem, then E is proportional to a certain quantity, which is the energy per particles times nu. So R would scale as the square root of nu. Okay, therefore, even if epsilon is small, nu is a very large number, and r is increasing, of course, as a number of dimensions, but as a square root. Therefore, I can assume that epsilon nu is much larger than r. Okay, because of the scaling. So now, basically, our omega now is v to the power of n. And then I have the integral of d3np, now not on a spherical shell, but this is the volume of a sphere of radius r. Okay, so here let's put Vr if you want, where Vr is the volume of a sphere of radius r in, well, in this case, 3n dimensions. Okay. And r is equal to 2me, square root of 2me. Okay. Okay, so now what we need to do is to determine this volume of a sphere in those arbitrary number of dimensions. So let's stop for a moment our microcanonical ensemble derivation, and let's come to geometry, and let's use some trick. Suppose that I have new dimensions, and consider this integral I equal to the integral from minus infinity to plus infinity of dx1 up to dx nu of a Gaussian, multidimensional Gaussian. Okay. Now this integral, of course, is simple as just the Gaussian, the result of a single Gaussian to the power of nu. So this is pi, square root of pi to the power of nu, if you want, is pi to nu divided by 2. Okay, and let's call this equation A. Okay, so it's just a Gaussian integral. Now, in new dimensions, the volume Vr of a sphere will be, as written before, a certain constant C And then let me maybe call it this small r in order to not to confuse with the capital R, which was for the square root of 2me. Let's be more general. So V of R is C times R to the power of nu, the volume of a sphere. So this is the volume. Whereas the surface of a sphere will be C nu R to the power of nu minus 1. So the same constant nu times R to the power of nu minus 1. This is the surface. Okay, so think about 3 dimension. In 3 dimension, you have the volume is 4/3 pi r to the power of 3, whereas the surface is 4 pi r to the power of 2. Okay, so these are well, just take the derivative of this and then you get the surface. Now, by noticing this, I can integrate I, so compute I in spherical coordinates. And so write I in the following way. In spherical coordinates, and by exploiting the symmetry, which is a spherical symmetry of this integral, I can write that I is the integral from 0 now to plus infinity of e to the minus r squared, which is basically this, okay, this r squared in spherical coordinates. And then I have, well, if you want, the Jacobian of this transformation and the integration over the solid angle, which will be, think about the spherical coordinates in 3 dimensions. Now we'll write the example, but it will be just the surface C nu r to the nu minus 1, and then I have a dr, okay? So in spherical coordinates in 3 dimensions, you have the integral of a certain quantity f of r from 0 to plus infinity of r squared, and then you have a 4 pi. 4 pi dr, ok?
Mi scusi, può scrivere un po' più grande?
Ah sì, certo, certo.
Grazie.
Okay, this is clear. What I wrote here is clear.
Yes, that one, yes.
Okay. Think about 3 dimensions in 3D. If you have a function having a spherical symmetry, the integral over the coordinates in the volume integral is f of r. Then you have the 4 pi coming from the integration over the solid angle, and then you have our r squared dr. Okay, so here we have the same structure. We have the function, which is a function just of r, and then we have, if you want, the surface here times dr. Okay, and here we have the surface times dr. Okay, let me change page. Okay, so so I have that I is equal to C nu, which I can put out of the integral from 0 to plus infinity, e to the power of minus r squared. Then I have r to nu minus 1, and then dr. Let me introduce a variable r squared equal to y, from which 2r dr is equal to dy. And therefore this is, so instead of dr, I can put dr is equal to dy divided by 2r, but r is the square root of y. And so I can here put c nu divided by 2, the integral from 0 to plus infinity of e to the minus y. And here you have a y to the power of nu minus 1 divided by 2. And then I have a dr, which was dy, and here you have a square root of y. See nu, let me see if this is correct, nu minus 1 divided by 2 and y. Okay, good. Now, this is also equal to c nu divided by 2 integral from 0 to plus infinity e to the minus epsilon, and then here I have y to the power of nu half minus 1, I would say, minus 1. And then this is dy. Okay, so minus 1 half is minus 1. Okay, now remember, and this is just the reason for which I have done it, the gamma of Euler, which was the following equation, described by the following, defined by the following equation. Gamma of z is e to the minus t, and then I have t to z minus 1 dt. So this is the Euler gamma. And then we also derived the fact that the gamma of n plus 1 is equal to n factorial. Okay? Now, if you compare this and this, you realize that this integral is actually c nu divided by 2, and this is the gamma of Euler computed in nu half. Nu half. Okay, so this is the gamma of nu half. For what is written there, the gamma of the gamma of n is equal to n minus 1 factorial, and therefore the gamma of nu half is equal to nu half minus 1 factorial. Nu half minus 1 factorial. And let's call this equation B. So we have computed the same integral in spherical coordinates, and we get c nu divided by 2, and then nu 2 minus 1 factorial. Now what we do is to compare A and B in order to derive which is the constant, the proportionality constant between the volume and r to the power of nu for the volume of a spherical shell in new dimensions. And this B and A was provided by pi to the power of nu divided by 2. Therefore, I can write that C is pi to the power of nu half, pi to the power of nu half, divided by nu half times nu half minus 1 factorial. Okay, which is also equal to pi to the power of nu half, and here I have a nu half factorial, because nu half times nu half minus 1 factorial is nu half factorial. Okay, so this is the constant C, and so I can write finally that the volume of a sphere in new dimension of radius small r is pi to the power of nu half divided by nu half factorial, and then I have r to the power of nu. Okay, so this is the volume of a sphere of radius r in new dimensions. New factorial and r to the power. sfera di raggio. Okay. Now we can go back. We can go back to the volume, so to the omega. And the omega was v to the power of n, and then we had this volume of a sphere well, this was 3/2, so 3n dimension. So we have a pi.
Prof, il
Sì,
foglio.
non ho cambiato pagina. Ok, scusate, non ho cambiato pagina. Forse l'ho messo qua adesso, sì, non so. Okay, so we have omega is equal to v to the power of n. Then we have this pi divided by, well, this pi. Then I have here nu half, but nu was 3n divided by 2, and then this 3n divided by 2 factorial, and then I have a 2me, which was the radius to the power of nu half, which was 3n divided by 2, where the radius, remember, it was 2me. This was the radius, and the nu, we have set nu to 3n because we have 3n dimensions. Okay, so with 3n momenta. Okay, this should be correct, maybe. Yeah, 3/2 d2m 3n. Okay, good. Now, okay, so this is the volume, well, is proportional to the volume occupied by rho in the phase space. Okay, because it's proportional because we set rho to 1 just for the sake of simplicity, and basically rho and omega must be proportional to each other. So there is a proportionality factor, but the volume occupied by rho, so the support of rho, is this function here, which is a function of n number of particles and total energy and volume, which were the three macroscopic variables. Okay, so these three macroscopic variables enter in a basically function which was derived from the microphysics, if you want, from the Hamiltonian. Now remember the Boltzmann equation, which is still the Boltzmann definition of entropy, which is still valid in this context. And we know that the Boltzmann entropy was provided by S equal to KB, the log of omega, where this omega was the number of microstates compatible with the thermodynamical equilibrium. In particular under the constraints B and fixed, which, if you want, is the case of an isolated system. Okay, so we have a macroscopic system with total energy, volume V, and the number of particles n. In thermodynamical equilibrium, you have a certain number of microstates, and Boltzmann says that the entropy, so the thermodynamical entropy, must be proportional must be equal to KB, the log of this number of microstates. Now, it's clear that omega, in turn, is proportional to omega, but is equal to omega, but a proportionality factor, but for a proportionality factor. Okay, there is a proportionality factor between number of microstates and the volume occupied by the microcanonical ensemble, okay? So this number of microstates, and this is the volume occupied by rho, by the microcanonical ensemble. They are proportional to each other apart from a density, if you want. No? If I count the volume and I have a density which will be exactly rho, I can divide the volume divided by the density, and this will provide a number of microstates. Okay. Now, for this proportionality factor, we will take care at the end of this, but for the moment, we just put in the entropy of Boltzmann the omega, the small omega. Okay, and then we will take care of the proportionality factor. So we can write basically that S is equal to KB, then we have the logarithm of this quantity here, and which was V to the power of N, then I have a pi 3n½ divided by 3n½ factorial and 2me to the power of 3n divided by 2. Okay, I will take care about the proportionality. Between the 2 omega later. Now, for the moment, we just insert in the logarithm of Boltzmann this function here. Okay, so we can already work out a little bit this expression. Where we are here. So we say that K, so S is KB. Then I think I can collect a factor of n outside. So I have n, and then I have the logarithm of V pi to me. So V pi to the power of 3 alpha, and then I have a 2me to the power of 3 alpha. Then I have a minus kb. So minus, well, I had minus kb, and here I have the logarithm of the denominator, which was 3 alpha 3 alpha n. Okay, 3 alpha n factorial. Okay, using the Stirling approximation, so Stirling, we can write this. Okay, this is the same, and then I have a minus kb, then I have a 3 alpha n, the log of 3 alpha n, plus kb times 3 alpha n by using the Stirling approximation. Therefore, the entropy is given by 3 alpha kbn, which is this term here. Then I have a plus kbn that I can collect. Then I have the logarithm of v. I have a pi to the power of 3 alpha. I have a 2me to the power of 3 alpha. And then I have 3 alpha n to the power of 3 alpha. So here I have 3 alpha to the power of 3 alpha. and then I have n to the power of 3 half. Okay, let me check if I have all the terms. I'm sorry. 3 half n kb logarithm of volume p to me 3 half n blah blah blah. Okay, that should be correct. Which is equal to 3 half kbn plus kbn logarithm of, now we have a volume, we have a ratio between E and N to the power of 3 half, and then what we have there is 4/3 m pi, 4/3 m pi to the power of 3 half. Okay, and then I think it's okay. So let me see, 3 half kb and kb log of v e to n 4/3 m pi. Okay. Okay, so at this point we have to notice something, that entropy, this entropy that we derived from the microcanonical ensemble by the definition of Boltzmann entropy, it has a term which is the term here, which is okay. And this term here is not really okay because of the following reason that will provide then a Gibbs, what is called the Gibbs paradox that we will analyze later. So here I have that S, apart from this term here, so it contains a term which is proportional to the logarithm of the volume. Now the thing is the following, that the entropy in such a form is not extensive. Because if you have two systems and you want to compute S1 plus S2, if you have a log dependence from the volume, basically you run into problems because you would actually basically do the log of V1 plus the log of V2 in the two cases, but this is not extensive, so it's not the sum of the two entropies. Okay, so if you have two systems with volume V1, volume V2, particles N1, particles N2, and energy, and you sum them, this is not the correct way to sum. So the variable is not extensive because this is extensive. Okay, but this is not extensive because you would have the sum of the two log. Okay. So because this S1 would contain a term with the log of V1, and you will get the log of V2, just because of that. Whereas in an extensive variable, when you sum the two systems together, when you add the two systems, you consider the two systems to be together, you just need the quantity which is proportional to the product of the sum of the volume and not to the sum of the log of the volumes. Okay, so for an extensive variable, we expect that S is proportional to the sum of the volume and not to the sum of the log of the volume. Okay. So this is a problem, and actually is a problem that provides a paradox, which is called the Gips Paradox, that we will analyze in a moment. Now, how to solve this problem? This is very tricky. But the trick, and this is very interesting, comes from actually quantum mechanics, and we will provide well, clear motivations when analyzing the quantum ensemble systems. But at this level, we just notice the following. You remember that in quantum mechanics, particles are identical and basically because of the absence of a way to distinguish the particles, the permutation of the particles provides the same quantum mechanical system. So there is no way to distinguish which is particle 1, particle 2, particle 3, etc. Okay, so actually, since the particles are identical, for instance, you know that the wave function of a system of fermions is normalized to the number of, with respect to the number of permutations of the particles. And here the situation is similar, and the deep reason actually comes from quantum mechanics. And so we have to provide a correction to this formula that we derived before and change omega to omega divided by m factorial, where this m factorial comes from quantum mechanics. And this basically tells you, let me change page, that when counting, so the fact that we substitute omega with omega divided by m factorial means that when counting the number of microstates, I can, well, I have to divide it by the number of permutations. Okay, I cannot distinguish particles, and therefore I divide by the number of permutations of those n particles. This procedure is called Boltzmann counting. And at this level, it is just, if you want, phenomenological. And will be derived later when we will do quantum statistical mechanics. Actually, this is a way, very interesting way to see how quantum mechanics somehow provides corrections also to quantities that are, in this case, classical, because we have a classical system, Hamiltonian, which is classical. We are not considering quantum particles, but we are forced to do that at this level in order to get an entropy which is extensive and not, as in this case, not extensive. Indeed, when changing the the omega, and we change omega into omega divided by n factorial, we have to basically, that means that in the entropy, we need to subtract a log of n factorial, okay, which is n log n minus n, which in turn is n log n minus n log e. So now what I do is to take the entropy that we have had before, which was 3 half nkb plus nkb log of v, then I add e to the divided by n to the power of 3/2. Then I have a 4/3 m pi to the power of 3/2, which was the expression that we derived before that we said is not extensive. So this is not extensive. And we subtract this term here. So I have a minus n log n minus n log n plus n log e. Then of course I have a kb, okay, in order to get the same dimensions. When doing that, I get that the entropy now becomes 3/2 nkb plus nkb can be collected, and then I have a log of v divided by n this times e divided by n to the power of 3/2 and 4/3 m pi to the power of 3/2. Let me close this, and then I have an additional factor of e. This should be the final result. So 3/2 nkb log of v divided by n, 4/3 e. Okay. Now you see that here we have v divided by n and e divided by n, which are intensive variables. Whereas before we had in the log an intensive variables, which was this, but an extensive variable. That's why before it was not fair, it was not, how to say, correct to some entropies, because we expect the entropies, the sum of the two entropies of two systems to be proportional to the sum of the volumes, which was not this case. But in this case, we have the possibility to sum entropies, because here we do not have now extensive variables, but intensive variables. So when we sum the entropies of two systems, we just have the extensivity, if you want, is in this prefactor, which is nkb, and all the variables inside are intensive variables. So when summing two systems, the intensive variables remain the same. So we don't need to sum them, okay? Now, this is one thing. So we have made, and then I will close in a moment. We have made the entropy as it should be an extensive variable. Now we have to correct dimensions. Okay, so now let me write again this quantity here. We have a 3/2 kbn plus nkb, and then I add the log of v.
La pagina, professore.
La pagina, scusate, salto in aria ogni volta, scusate. Let me write again this expression. Well, actually, let me write just the log of what we had there. We had the log which contains a v divided by n. Then I have e divided by n to the power of 3/2. Sorry. There is a 3/2 missing here. There is a 3/2 missing. So this is 3/2. E divided by n to the power of 3/2. Then there is a 4/3 m pi to the power again of 3/2, and then e. Okay, b, e, n, blah, blah, blah. Okay, so now let's make, since from the beginning we said, okay, let's put in the log the small omega and discuss the proportionality with this capital omega later, we have now to take care about the dimensions, okay? And let's do it. So before we have corrected the entropy in order to have an extensive entropy as it should be, and we said that this correction comes from quantum mechanics, basically. And we will derive this later in a few weeks. For the moment, we just remember that particles in quantum mechanics are indistinguishable, and therefore permutations over those particles provide the same system, must provide the same system. Now let's analyze the dimension of what is inside here. Here you have a volume divided by n, so these are from the dimensional point of view. I have a length squared, then I have e to the power of 3/2. Now e to the power of 3/2, what is e is a mass, then to the power of 3/2, and then I have a length divided by time, which will be a length divided by time to the power of 3. Because it's a mass, so energy is mass velocity squared, so it's L divided by time, so length divided by time to the power of 2, but here I have a 3, and then should be LT to the power of 3. And then I have another mass to the power of 3/2, which is basically another mass to the power of 3/2, okay. So then we had the length to the power of 3, mass to the power of 3, length to the power of 3, mass to the power of 3, and then I have a length to the power of, divided by time, to the power of 3 again, okay? So I'm getting confused. This should be, let me see if I got correct these numbers. This should be length to the power of 6 m cubed and t cubed, which is also L to the power of 3, to the power of 2 m t to the power of 3. Okay, this should be correct. So it's a length squared times mass divided by time to the power of 3. This is what we have in the dimension of the log, which of course is not nice, because a log should have a quantity which must be a-dimensional. Now, what is this? What is the dimension of an action? The action is energy times time, which is a mass length divided by 2 to the power of 2, and time here. Okay, so an action is mass L squared divided by t. So what we actually have here is an action to the power of 3. Therefore, in order to have an argument which is adimensional, argument in the log, I have to divide by an action. Okay, so let me write again the entropy. So it's 3/2 nkb plus the log of all these quantities here. So okay, nkb times the log, and then I have a b divided by n, e divided by n to the power of 3/2, 4/3 m pi to the power of 3/2, then e, and let me divide here by an action, and let's call it 1 over h cubed, where h is the dimension of an action, in order to satisfy the fact that the argument of a log must be a-dimensional. Okay. Now, what is this action here? Of course, now we cannot know at this level, but we will be derived later, At this level, we just know that we have to divide the argument of the log, the previous one, by an action, a quantity, which is the dimension of an action. What is this action? Well, it's the fundamental action of quantum mechanics, which is the Planck constant. Why we have a Planck constant here? Well, this as I said, will be justified in statistical quantum mechanics. At this level, we just need to remember that in the phase space, if you want, the volume occupied by a particle is basically h. So when counting the number of microstates, I have to take the volume of the phase space, divide by m factorial, okay, is omega, in order to take into account the indistinguishability of the particles, and also divided by h to the power of 3 in order to count really the number of states, because each state occupy a volume h to the power of 3. But as I said, this will be justified in a better way later. At the moment, we just know that we need to introduce an action there, and this action is, by the way, just the Planck constant. And we know, of course, some quantum mechanics, and we know that in the phase space, the Planck constant provides, if you want, the volume of a single particle state. Okay, so I would say that we stop for 5 minutes because it's already 10:15, and then we gather in in 5 minutes or so. Okay.
Prof?
Sì,
Scusi,
sì,
I have a question.
yeah.
I think I lost myself at some point,
Mhm.
and I didn't get why, when we were computing the integral of omega,
Mhm.
we said, okay, now let's focus on the geometry, and we took the integral of a Gaussian.
Mhm.
Why did we do that?
Okay, this is just a trick. So the thing is that, yeah, I can write here. If you have a new dimension, you expect the volume is a certain constant that is a geometrical factor and
Mhm.
r to the power of nu. Okay.
Mhm.
Now, what is the value of c? We don't know, and the passing through this integral is just a trick, a mathematical trick, in order to find c, because this integral that we have written in this way is the Gaussian, no, x
Yes.
nu squared. This can be done in two ways. Is the same technique that you use to, for instance, to compute the Gaussian integral. It's the same technique, no? If you do that, this integral
Okay.
from minus infinity to plus infinity to the minus x squared dx, to do that, the trick is the following: you take the square root of this guy times this guy here,
Yes.
e to
Yes.
the minus y
Okay.
squared dy.
Okay.
Then this is the square root of the integral from minus infinity in dx minus infinity plus infinity dy of x minus x squared plus y squared. Then you go to spherical coordinates,
Coordinates,
no?
and then
And
that's
you
the
say that
radius.
exactly. So then you can write this as an integral from 0 to plus infinity over dr of 4 pi r squared.
Okay.
Sorry, it's not correct. This because we are in two dimensions, and in two dimensions you have the Jacobian is r, okay, and
Okay.
here you have r squared, and then you should have a factor of 2 pi.
Okay.
Okay.
Okay. So we just compare that as
Exactly.
okay.
So
Okay.
you do this integral, which is a Gaussian integral in Cartesian coordinates, for which
Mhm.
you know the result already. And then you compute it in spherical coordinates. You compare the two things because they have the same. Well, in the second case, so in the first case, you do the integral, you know the result is nu to the power of nu half. In the second case, you don't know the constant that appears in spherical coordinates,
Yes.
and by comparing the results of this of the same integral but computed in two different ways, you can derive this constant.
Okay. Perfect.
Okay,
Thank
so
you.
this is a mathematical trick.
Okay.
Okay.
Thank you very much.
Yeah. So on that, of course, now we said that. Just let me make a comment that I forgot to say. We said that the volume in new dimension of a sphere is nu half. So it's pi to the power of nu half divided by nu half factorial times 3 to the power of nu. And of course, now you can guess that for nu equal 3, which is the three-dimension case, we are in troubles. But actually, this is not true, in the sense that this pi to the power of 3 half, r to the power of 3, and then I have a 3 half factorial. Now, the 3 half factorial, of course, is something which is not a normal factorial, but is a gamma function, the Euler gamma. We said that the Euler gamma has these properties that gamma of n plus 1 is equal to n factorial, and therefore the gamma of 3 the 3 half factorial is actually the gamma of 5 half, okay, by using this equation. Now, what is the gamma of 5 alpha? 5/2, sorry, you go, for instance, to Mathematica, or you go to Wolfram, or I have to write Wolfram, I don't remember, like this maybe. Wolfram alpha. You know what is Wolfram alpha, right?
Yes.
Yes, yeah. And you can use the gamma, the Euler gamma is tabulated, and the gamma of 5 half is equal to 3/4 square root of pi. And therefore this is correct, because in 3 dimension you will have a pi to the power of 3/2, then you have a 3 divided by 4 square root of pi and r to the power of 3. And of course you get the correct result, which is 4/3 pi r to the power of 3. No, because 3/2 minus 1/2 is 1. Okay? But so this is just geometry, and the fact that we took these two integrals was just it's just a mathematical trick, okay, in order to find this proportionality constant. Okay, so I think that we derived the final formula for the entropy that we will write and discuss a little bit further now. And so let me change page. So we say that the entropy is equal to 3/2 nkb plus nkb logarithm of v divided by n, e divided by n to the power of 3/2. And then I have a Euler e h cubed, and then I have a 2m pi divided by 3/2 to the power of 3/2. Okay. Now this formula is not very nice written in this form, but we will write in a slightly different way in a moment. Now let's make a little bit of thermodynamics now. This is we know from thermodynamics that the derivative well, let me write back again an equation that we know. TdS is equal to PdV plus du, or dE in this case. Therefore, if I do the partial derivative of S with respect to E at fixed volume and fixed number of particles, in principle, I should get 1 over the temperature. Okay, so let's do it. So let's derive S with respect to E at fixed volume and number of particles. This is 1 over T. And so deriving this expression with respect to E means that we have to do nkb okay, so maybe it's better to do this, okay, first, otherwise we get in confusion. Okay, so this is 3/2 nkb plus nkb. Let me write this in the following way. I have the log of E to the power of 3/2, and then I have something which is let me call it K. Okay, this is just because I'm doing a derivative, so I'm singling out the variables with respect to which I'm going to make a derivative. Okay, so it's 3/2 nkb plus nkb log of E to the power of 3/2 times a certain quantity that is not important for the moment. Now, when doing this derivative, of course, I get nkb well, times 3/2 that I can put now here. And then I just have E, okay? Sorry, 3/2, sorry. Okay, so maybe let me be more clear, otherwise you don't understand, sorry. Okay, let me do the following. So I had to do the derivative with respect to E of this quantity, 3/2 nkb plus nkb logarithm of E to the power of 3/2 times k. Okay? Now this is equal, the first term does not contribute, the second term you have, if you want, an nkb outside, and then you derive the log well, actually it's much better to do this before, nkb log of E to the, and then the 3/2 you put it outside, plus nkb log of k, by just using the the logarithm properties. And so when doing the derivatives, you just have 3/2 nkb and the derivative of the logarithm, which is 1/e. Therefore, what we derive is that 1/t is equal to 3/2 nkb 1/e, from which we get that E is equal to 3/2 nkb t. Okay? Now this is interesting because this is the total energy, and is 3n times 1/2 kbt, which is known to be the Agri-Partition Theorem, no? That we will repeat and we will derive again, but you might remember that basically this is the Equipartition Theorem. Equipartition Theorem. So each degrees of freedom, quadratic actually degrees of freedom, contributes to the total energy with a kbt divided by 2. Okay, since you have 3n independent momenta, you have 3n times kbt divided by 2. And similarly, so we are now deriving thermodynamics from statistical mechanics. We can compute the derivative of S with respect to the volume by fixing n and E, and this is equal to P divided by temperature. And now, as you see from the previous equation, when deriving, so S was 3/2 kbn plus, again, let me use the same trick as before, nkb, then I have the logarithm of volume times a constant. Okay, so when I do the derivative of S with respect to the volume, I just have nkb divided by the volume. Okay, so this is nkb divided by the volume, and this is equal to P divided by T, from which we get the PV is equal to nkbt, which is nothing but the ideal gas equation of state. Derived from statistical mechanics. Or if you want, from microphysics. Okay. These are very interesting results. Consider that we are, okay, this is the most simple system, of course, which is a system of n particles in a volume V with a total energy, non-interacting particles. At the microscopic level, non-interacting particles means that the Hamiltonian contains just the kinetic terms, okay? So once we fix the Hamiltonian of those particles, by using the microcanonical ensemble, which means basically to compute the volume occupied by the phase space, in the phase space by the ensemble itself, and then we can get the entropy from the Boltzmann definition of entropy, and from entropy we can derive all the thermodynamical quantities. Okay? So indeed, in the final formula, it's better to write this equation of entropy that we derived in the following way. We have 3/2 nkb plus nkb logarithm of v divided by n. And then I have Euler E. And then we had E divided by n to the power of 3/2, which is equal, by considering the fact that E was equal to 3/2 kb and t, so E divided by n is actually 3/2 kbt. And therefore here you have 3/2 kbt, 3/2 kbt to the power of 3/2. And then we have additionally 2m pi divided by 3/2 to the power of 3/2. And I think I have everything now. And then I have an additional h to the power of 3. I think I have everything now. So it's v divided by n, e divided by h, 2m. Okay, that's correct, I think. Now I can remove this 3/2 and this 3/2, which are to the power of 3/2, both of them. And let me change page. And finally, we get the following formula, that S is equal to 3/2 nkb plus nkb log of v divided by n. Then I have foglio, okay. S is equal to 3/2 nkb plus nkb logarithm of v divided by n. Then I have an e. Then I have a 2m pi kbt divided by h squared to the power of 3/2. Okay, let me check if I have all the terms. Okay, so it's 3/2 nkb and kb logarithm of v divided by n, a 2m pi kbt h squared to the power of 3/2. Now this formula is called the Sakur, just if you want to remember the name, tetrode formula. For the entropy. And it's something that you never see in thermodynamics, because in thermodynamics you just deal with the difference of entropies, whereas this is the absolute entropy, if you want. Once you fix the temperature, once you fix the energy and the number of particles and the volume, or the temperature instead of the energy, you can compute the entropy, the absolute entropy of a gas of particles. So this is ideal gas again, okay? It's very useful to define this quantity, which is h divided by 2 pi m kbt, that we will use many times. This is called thermal de Broglie wavelength. And in such a case, once you introduce this quantity, which of course contains the temperature and the H, so it contains thermodynamics and quantum mechanics, and this is a very important quantity because it allows us to define which is the classical regime and the quantum mechanical regime. Then S is equal to 3/2 nkb plus nkb logarithm of E times v divided by n, which is still there, and then I have 1 over lambda squared, lambda cubed, of course, okay? So from which you see that here you have a ratio between the volume, the total volume occupied by the gas and the volume provided by the thermal de Broglie wavelength, which is, if you want, the volume occupied by the wave function of a particle at a certain temperature. Okay. Let me see if there is another thing that I need to compute. Well, actually, this also can be written as a 3 alpha nkb plus nkb logarithm of E, and then I have product of n lambda squared, where n is the number density. Okay. Okay, good. So now this equation for the entropy, this one, is correct when we are in the classical limit. What is the classical limit? The classical limit is basically provided by the following equation. N lambda cubed much smaller than 1. So this is the classical limit. Which means that the density is much smaller. So the density of particles, if you want, is small, or well, it can be interpreted in different ways. These equations holds true since lambda is proportional to 1 over square root of temperature. This is true when the temperature is large. Okay, so temperature large, low density, or if you want H, if you want to interpret in terms of semi-classical theory, or that H is very small. No, but okay, I prefer to talk about large temperature, because for large temperature lambda is small, and small density, because in this case n is small, and of course the product of n lambda cubed is much smaller than 1. Why I take n lambda cubed? Because this is clearly an adimensional quantity, which is proportional to the ratio between the volume occupied and the gas. Well, the volume per particle and the volume given by the thermal de Broglie wavelength. Okay. So this formula of Sackur tetrad for the entropy of an ideal gas at finite temperature in the classical limit, is a statistical mechanics formula, cannot be derived in thermodynamics, and it has been, of course, tested with experiments. And of course, the corrections, the phenomenological corrections that we have done, what Boltzmann has done by introducing the Boltzmann counting, and by also introducing the Planck constant in order to make the argument of the logarithm adimensional, has been tested by experiments, if you want. Okay, So this is a correct formula that was derived in a phenomenological way, if you want, but it has been tested as it should be. Okay, now in the last 10 minutes, if I have time, I will explain you the Gibbs paradox. That is, again, something connected to the fact that the entropy that we derived without the Boltzmann counting was not extensive. And the fact that we do not have an extensive entropy provides some weird fact as the Gibbs paradox. So let's talk about the Gibbs paradox. So we have the entropy written is 3 nkb. Well, this term is not important actually, but in any case, nkb, then the logarithm of v times 4/3 m pi to the power of 3/2, and then let me introduce a quantity u to the power of 3/2, where u is defined to be e divided by n. Okay, so this is without Boltzmann counting. Okay, and also without the correction due to the h to the Planck constant. Now suppose that we have a system which is a typical system in which we have n1, v1, and v2 and 2, a box. This is a barrier. And suppose that we have two gases here, monoatomic gas with the same density. So suppose that N1 is equal to N1 to V1 is equal to N2 and V2, and suppose also that the two gases are at the same temperature. So two monoatomic gases at same temperature and density. Okay. The formula that we derived before, of course, is the case of a monoatomic gas because we have just 3 degrees of freedom associated with the 3 momenta. Okay. The 3 kinetic energy, if you want. Well, the 3 momenta, better to say. We will analyze later also the case of diatomic molecules, etc. Okay, now if N1 is equal to N2 and the temperature is the same, also the energy density is the same because U1 will be equal to E1 divided by N1, but E in general is 3/2 kBTN. We derived it before. Therefore, the ratio between E1 and N1 is just the temperature. Okay, so this E2 N2 equal U2. Okay. Okay, so now let's compute the total entropy before we remove the barrier. Before removing the barrier. The total entropy will be the sum of the two entropies, S1 plus S2, which is equal to, 3/2 kb, and then I have N1 plus N2 plus N1 kb logarithm of V1 times, let me call K, the quantity 4/3 m pi 3 to the power of 3/2 times u to the power of 3/2, which is the same for the two gases. For the two components. Okay, so this is a logarithm of V1 times K. And then I have a plus n2 kb log of v2k. Okay. So this is the total entropy of the system before removing the barrier. I don't know why. It's not charging. Facciamo così allora. Now remove the barrier, and let's write it the total entropy again. Well, this will be 3½ kb, again the sum of the particles, n1 plus n2, plus n1 kb logarithm. Now instead of v1, I should put v, because the total volume, which is which the gas 1 can occupy, is not v1, but can be is v now, plus n2 kb log of vk. Okay, so now if you compute the difference in entropy before and after, after and before the removing of the barrier, so delta S, so after minus before removing the barrier. Foglio. Okay, delta S, which means after minus before removing the barrier. Well, this difference in entropies, delta S divided by Kb, is equal to, well, you can just work out the calculation is just equal to n1 log of the final volume divided by the initial volume, plus n2 the log of the final volume divided by v2, and of course this is larger than 0. So you have an increase of entropy. Okay, as it should be, because you have two gases which are different in principle, although monatomic gas, and you remove this barrier, and there is in practice there is a mixing entropy, what is called a mixing entropy. So the fact that before the particles in one were characterized by a certain quantity, the color, for instance, we will do an example. The particles on the right-hand side were characterized by another quantity, by a different color, for instance. Now you mix them together and the entropy increases, okay? So you have white, well, red and blue at the beginning, and after you have red and blue, but mixed in a volume. So this will correspond to an increase of entropy. But actually here comes the point. I will get the same result if the two gases are actually the same. So consider a box with a barrier, well, with a gas, then I put a barrier, then I remove this, and by removing this, it seems like that the entropy is increasing, although haven't done anything on my system, okay? Because in the formula that we just used, there is no, if you want, there is no information about the fact that the two gases are different or the fact that they are the same. There is no information on that. And so removing this barrier provides an increase of entropy, even if the two gases are the same. And this is the so-called Gibbs paradox. How to solve this paradox? Well, the paradox is solved once we adopt the correct formula for the entropy. So the entropy was actually 3 kb, 3 half kb, and then it was n kb logarithm of a certain constant k divided by the density. Okay, and I think that we will continue with that next time, because now it's almost 11. But if you want, you can try to do it as an exercise. So to try to show that when adopting this formula here for the same gas, you get 0. You get that the delta S is equal to 0. Maybe just a comment on that, and then I will close. Why so? The initial entropy is the sum of the two entropies. And of course, this is, well, the 3 half kb n1 plus n2 plus n1 kb logarithm of b1 divided by n1 times constant c plus n2 kb logarithm of v2 divided by n2 times the constant. So this before. After, I have the total entropy is 3 half kb n, where n is n1 plus n2, plus, here I just have one gas, so I have just n kb logarithm of v divided by n times c. Because I have just one gas, I do not have to distinguish between number n1 of particles, number n2 of particles. I just have one gas occupying a volume v with the total number of particles n. Okay, so now when I do, so suppose that is after and this is before, delta S, which is equal to the entropy after and the entropy before, I have a n kb logarithm of v divided by n times c minus n1 kb logarithm of v1 divided by n1 c minus n2 kb logarithm of v2 divided by n2 c. Here I close, you can show that this is 0, because v divided by n is equal to v1 divided by n1 is equal to v2 divided by 2 is equal to n. Well, 1 over n, sorry. Because the density is always the same. Okay, so let me close because it is 11 and maybe Luciano is already there. So I'll see you next Tuesday.
Thank you. Bye bye.
Ciao.
Arrivederci.
Bye.
Arrivederci.